Hi, today we are looking at continuity. So there is three conditions of continuity. So we can say a function f is continuous at x equals a if our function exists at a, if our limit of f of x as x approaches a exists, and if our limit of f of x as x approaches a is equal to our function at a. So we'll look at an example of things that are not continuous nets and talk about why they aren't. So we have this graph here, and we want to explain why if a function of f is discontinuous at x equals -3, 2, 3, and 8. So we'll start by going left to right. So we'll start with x equals -3. So at x equals -3, what we can see is our limit as we go from the negative side is at +2, while from the right side or a positive side, it's at 4. So we can see those limits do not equal each other from the left and right. So therefore, our limit of f of x does not exist as we approach -3. So we can say our limit of f as x approaches -3 does not exist. Now, this type of discontinuity, because we're going from here jumping up to here, is referred to as a jump discontinuity. Next, we'll look at x equals 2. So at 2, as we approach from the left, we go towards -infinity. As we approach from the right, we're also going to -infinity. However, because -infinity is not an exact value, that limit technically does not exist. So our limit of f as x approaches 2 does not exist because it is going towards -infinity, which is not an exact value. Now, this is known as an infinite discontinuity. Okay, so next we've got at x equals 3. So as we approach 3 from the left, we see that our y value is 3. As we approach it from the right, our y value is 3. So our limit does exist. However, our function at 3 is at 5. So our limit was 3, our function is 5, so our limit does not equal our function. So we can say our limit of f as x approaches 3 does not equal f of 3. Now this is known as a removable discontinuity. And lastly, we've got x equals 8. So for 8, we can see that as we approach from the left or from our negative side, we get the same value as if we approach from our right or positive side. So our limit does exist. However, we can see that nowhere on 8 does our function exist. So we can say f8 does not exist And that's the same type of discontinuity as this previous one. Okay, next we're looking at sketching a graph, and then we're going to find all values of x at which f of x is discontinuous and find the limit of each at their points of discontinuity. So we've got f of x equals x plus 2 over x squared minus x minus 6. So I'll just start by rewriting our equation down here. So we've got f of x equals x plus 2 over x squared minus x minus 6. So we'll start by factoring. So we've got f of x is equal to x plus 2 over x minus 3 times x plus 2. So looking at this, we know that x cannot equal 3 or negative 2. So we can say it's discontinuous at x equals negative 2 as well as 3. Now, we can see that this cancels. So essentially, we've got f of x equals 1 over x minus 3. So we will plot this graph, but first we're going to mark in our asymptotes. So we can see from this initial equation, the degree of our denominator is larger than our numerator, so we have an asymptote at x equals 0, or sorry, y equals 0. And then one of our non-permissibles canceled out, buffer did not. So we've got 1 over x minus 3, so that did not cancel. So therefore, at positive 3, we have a vertical asymptote. Now we're going to find our hole, because our non-permissible, it canceled out, it's going to give us a hole. So I'll put f of negative 2 in. That gives us 1 over negative 2 minus 3. So 1 over negative 5. So we have a hole at negative 2, negative 1/5. We have a hole there. Graphing this reciprocal of a linear function, we should have something that looks something like this. Now we want to find the limit of f at each point of discontinuity. So our limit as x approaches negative 2 of f of x would be our limit as x approaches negative 2 of our function that's remaining here. So of 1 over x minus 3, that'd be 1 over -2 minus 3, so -1/5. Now our limit as x approaches our other point of discontinuity, so x approaches 3 of f of x, is going to be our limit as x approaches -2 of 1 over, or sorry, as approaches 3 of 1 over x minus 3 is the same as 1 over 3 minus 3, which does not exist. And we can see it shouldn't exist from here because we're going towards positive infinity from the positive side and negative infinity from the negative side. Next example, let f be defined by f of x is 2x plus 3 where x is less than 1 and x squared minus 6x plus 10 where x is greater than 1. We want to use the three conditions of continuity to prove that f is continuous at x equals 1. So first, we need to exist at an x value of 1. So if we have f of 1, x is 1 with this function here. We can see if this one, it doesn't have equal to, so therefore we'll be substituting our 1 into this equation here. So we'd have 1 squared minus 6 times 1 plus 10 and that gives us 5. Second, we're going to show that our limits give us the same value. So first we've got our limit of f of x as we approach x, or sorry, approach a value of 1 from the negative side. So if we're below 1, then that's going to be this function here. So we're looking for our limit of 2x plus 3 when x is approaching 1 from the negative side. Now, because this is just a polynomial function, we can just substitute our 1 directly in for it. So this would be 2 times 1 plus 3, which gives us 5. Next, we'll check that with our limit from the right side. So limit of f of x as x approaches 1 from the positive side. So from a positive side, we are using our x squared minus 6x plus 10. So we'd look at our limit of x squared minus 6x plus 10 as x approaches 1 from the positive side. So that would be 1 squared minus 6 times 1 plus 10, which gives us 5. So this limit does exist. We can say our limit of f of x as x approaches 1 is equal to 5. Now, third, our limit of f of x as x goes towards 1 gives us the same value as f of 1. Therefore, because it's met these three conditions, f of x is continuous at x equals 1. Okay, next example, we want to find the value of k that makes f continuous everywhere, and we're given f of x is equal to x squared plus 8x plus 15 everywhere except for x equaling -5. And then our function is equal to k when x equals -5. So in order for f to be continuous at x equals 5, I'm sorry, I just realized that I did make a mistake when I typed this out. So before going into what makes this continuous, this was supposed to be a rational function. So I'm just going to write in what that should have been. So it should have been x squared plus 8x plus 15 over x plus 5, which is why we have everywhere but x cannot equal -5. Sorry about that. So in order for f to be continuous, at x equals 5, or sorry, x equals -5, our limit as x approaches -5 of f of x must equal f of -5. Therefore, our limit as x approaches -5 of f of x must equal f of -5. So if we go limit as x approaches -5 of f of x, that equals our limit as x approaches -5 of x squared plus 8x plus 15 over x plus 5. So that's equal to our limit as x approaches -5 of what I want to do is factor this. So that becomes x plus 5 times x plus 3 over x plus 5. Now what we'll notice is these cancel out, which leaves us with our limit as x approaches -5 of x plus 3. Now we'll do our direct substitution, so that'd be -5 plus 3, giving us -2. And therefore, k must equal -2.